Hello, in this video, I am illustrating how to perform lab on torque and equilibrium. So there are two kinds of equilibrium. One is the equilibrium of forces, in which we call net force is equal to 0. That is, look at here, the sum of the forces should be 0. That is the first condition for equilibrium. So in mathematics, we can write down sum of all the forces. This symbol, which is the Greek letter sigma, sigma f, that is we call summation f equal to 0. That is the first condition of equilibrium right here. And second condition of equilibrium is the sum of the torque caused by the forces must be 0. So torque is denoted by tau. This symbol right here is Greek letter tau, is said to be tau, tau, and total torque, the sum of the torques should be equal to 0. So these two conditions are the conditions of equilibrium. If these two conditions satisfied, then we can say a system or particle is at equilibrium. If one of them is not satisfied, then the system is not in equilibrium condition. Okay, so in this video, I will guide you how to do the torque and equilibrium lab. Mainly, we are gonna to check second condition of equilibrium. Okay, we are not talking about this one. We are not applying several forces and equilibrium conditions, but we are measuring some torques on a system, and a total torque will be 0 to have an equilibrium condition. Okay, so that's what we are doing. So to get started, just go to the link given here, open the hyperlink torque and equilibrium condition. Once you press on it, you will get this window, and let me refresh this one, and initially you will get this kinds of window. So click on the boxes behind the forces from the object's mass, and the labels is already there, and the label, it will give you the label, so that we will see the equilibrium conditions, and ruler here, so that we can measure the distances from the pivotal points right here. Okay, so also here are two supports. If you put the mass over here with these two supports, this ruler will not move, right? That's why we have to choose this one. Right now the system is at equilibrium condition because mass is perfectly balanced. Right hand side and left hand side is equally balanced. The symmetric condition is here. That's why it is equilibrium condition. Okay, so to get started, you can put the masses here. Our goal to measure right here in this lab is go to the table 1. In table 1, you can look at different parameters you have to measure in this experiment. Look at here. In first column, mass of the right, you have to measure the mass of the right side, and mass on the left side, right, right, that is the distance from the center point to where you put the mass, and r left is the length, that is the distance from the center to the right, to the left, at which you kept a mass. Okay, let me go back to the lab and put some mass. Okay, so for example, this is the right. Okay, this is the right, and this is the left. Okay, let me put certain mass on the right. For that, mass right, let me pick up 5 kg from here and put it here. Okay, right now you can see this is not a balanced or equilibrium condition. That is non-equilibrium condition, right? It is slanted, it makes certain slope. Now take 10 kilograms somewhere and try to put somewhere to make the balance. It's not. Let me try some other position. If I put it here, if it becomes balanced, it's not again. And let me get exactly put it on 1. It makes or not. Let me check. Maybe I have to move this direction. Okay. It looks like it's coming closer. Put it here and wait for a moment. Yes, it indicates the balance, right? Look at here. I put 5 kg over here. I put 10 kg over here. So this is the right. This side is the right side. This side 5 kg one, and left side is 10 kg one. So let me write it down on this one. So mass at the right was 5 kilogram, and mass on the left is 10 kilogram, right? So right is 5 kilogram, left is 10 kilogram. Okay, so let me go back and measure the distance from the center. Okay, so look at here. This is the central point from here, which is 0, right? Starting from here, it is in meters. 0.25 meter, 0.5 meter, and it is exactly at 1 meter, right? So right is 1 meter. The length from the center to the right is 1 meter. Okay, so what is the distance from the center to the left? This distance, this is 0.5. So 0.5 meter. So units are in SI system. Mass is measured in kilogram and distance is measured in meter. So we don't have to convert it into another system. So let me go back and put the values, those values. Okay, so our value here, that was a 5 kilogram, 1 meter, which is 10 kilogram, and this is 0.5 meter. Okay, so this is the first set of data. Now try to repeat the experiment with different masses, so that for every mass the this law, that is law equilibrium condition, is satisfied. To check that, let me go back to the experiment window and let me put it back all here. At this time I'm doing just opposite. The less mass I'm putting here in 1 on the left. This is the left, and more mass, maybe I will pick up 20 kg and try to balance it. It is unbalanced. If I put it here, it is again unbalanced. Let me try here. It is unbalanced. Let me try here. It is balanced. Let's try to put somewhere else. It first data we put on 1 meter in right and 0.5 half meter on the left. Let me try some other points. For example, if I put this one at 2, what will happen? Okay, on the left I put 10 kg on 2 meter distance from the center, and let me balance it. It's too much. Come on, let's see. Wait for a moment until balance. Yes, it is the perfect balance, right? Look at here. This is the label. It is labeling. It's perfect. Until this shows color, just wait until balance is perfect. That is the uh, uh, equilibrium condition, right? The sum of the torque is equal to 0. So now look at here. What is the what are the masses right now? This is right. In right we have mass of 20 kilogram. What is the distance here from here to here? This is the 1 meter, right? 1 meter. And on the left, the left arm length is 2 meter from the center, and mass here is 10 kg, right? M left is 10 kg. So we have two data. Let me go back and put the data here. So it was 5, that was first data. 1 in the right, 10 kilogram, 0.5. And second data was 20, 1 meter, 10, 2 meter, right? That's what we get. So similarly, you can do the different set of the masses and make the balance. That is the equilibrium, torque equilibrium condition. Okay, so there are several other data. You can take it. I'm just taking two data and calculating the torque, and whether our data is correct or not, we will see. After calculation, we will be able to check it. Okay, so let me go down to do further calculation. Let me go to the second data table. Look at here, data analysis is here. To find the mass, no, force on the right, what you can do, you have a mass on the right. For the first data, mass is 5 kilogram, and what is the force? Force is equal to mass into acceleration. In this case is the gravity, m into z, right? F equal to mg. So mass is the 5 for the first data, and 9.8. What is this? So this will come, let me do some calculation over here. Just a moment. Okay, so it is 5 multiplied by 9.8. It is giving me 49. So I can write down 49 here. And F left is, on the left, mass was 10 and 9.8. It gives you 9.8, right? And also for the second one, second data, mass on the right was 20, and 20 into 9.8, 20 multiplied by 9.8 will give you 196, right? And then on the left, 10 into 9.8, so 10 into 9.8 will give you 98. I'm writing down 98 here. So F left is not 9.1. How much should be there? It is 98, right? So I have to erase this decimal. So 9.8, 98. Okay, so these are force on the left arm, and these are forces on right arm. Now our goal is to find a torque on left and to find a torque on the right? So what is the formula for torque? Tau right, this one, right? First of all, this right is F right multiplied by R right. If we put formula for this one, F right is 49, and for first data, if you remember, that was 1. The distance R right was 1, right? This value was 1. So multiplied by 1, it will give you 49. Okay, so I can write down 49 here. So for the left, force is 98. So I can write down 98 for the F left. Okay, F left. multiplied by r left is 0.5. So if you multiply this one, you will be getting 49. 49, right? Look at here. Tau, which is the torque on the right side of the balance, is equal to tau, that is the torque. What is torque actually? That is the turning effect, right? Because of the turning effect, the particles, the system rotate. The balance right here rotates. So we get 49 and 49. It's a good results. Let us do calculation for second part. I mean second data. Okay. So force on the right is 196 multiplied by what was the distance? Distance was 1, right? R right. So which gives you 196. So for the left, so F left, and let me write it down here, 196 on the right, and this is for the left. So F left was 98, and what is the distance? R left, that was 2. If you multiply 98 with 2, it will be 826 and then 19, 196. Look at here, we get exactly same value, right? So from here you conclude that left-handed torque, right-handed torque is equal to left-handed torque. Right-handed torque is equal to left-handed torque. Our condition is verified, right? If two torques are equal, that is the equilibrium condition. So tau right is equal to tau left, L, right? So if I rearrange this equation, tau right minus tau L is equal to 0. That is, this is sum of the torque, right? Summation tau is equal to 0. So condition of equilibrium is verified by experiment. When system is in equilibrium condition, total torque acting on that system is equal to 0. Okay, you can do other data. Similarly, you can choose this several different set of masses, for example 10 kg, 15 kg or more. There are many other choice you can choose, and let me show you something else. This is done. Before drawing a graph, let me show you here. To choose the masses, if you go here, there are different people having different weights. Look at here, masses, you can choose from anywhere. So one more thing you can do from this experiment is, if mass of something is unknown, you can find it out. How? Let me do that. So put it back, right? So suppose that you don't know the mass of this B, unknown B, we don't know, right? To find the mass of this unknown B, let us try to balance it. Let me go back and grab. Okay, is it 5 kg? Wow, it's 5 kg, not 5 kg. Yes, 5 kg, because it is equal distance, right? So you can easily calculate, because you have a definition, right? Tau left equal to tau right. What is tau right? R distance right into force, distance right, left, this is right, this is right, this is left, right, this is force is left, right? So distances are equal. We put here 1 meter at 1 meter and here is 1 meter. So 1 meter and 1 meter cancelled. Force will be equal. So force right is equal to force left. So what is force? M into Z is equal to M right, M into left, Z. Z will be cancelled. Z is same thing, right? So mass of right should be mass of left. So 5 kg is equal to 5 kg. To get here, this is the powerful tool to find the unknown mass if you know the balance. This is the principle how we measure, how we compare masses, right? That is this balance that we use in daily life. Okay, so before finishing this lab, let me show you something else here. So you got data like 49 here. How much was the 49, right? And 49 here, and 196 here, and 196 here. So finally you have to draw plot between left and right torque. Suppose that you put the left torque here and right torque here, tau right? So what will be the graph? What will be the nature of graph if you draw plot, right? There are several datas. I just have a 2 points. I'm just drawing for 2 points. Suppose that this is 50 and this is 100, and then let me elaborate this one little bit, okay, so that it will be more easier for me to draw. Okay, suppose that this is 50 and this is 100, this is 150, and this is 200. Okay, this is 300. Similarly, I can put it here 1 2, this is 50, this is 100, this is 150, this is 200, and this is 250, right? So this one also 250. Okay, so now plot. So 49 means somewhere here, right, near 250, that is 1 point, and my another point will be somewhere nearby 200, which is 196, and it will be somewhere here, this is below, not right here, this somewhere here, right? If you draw a line from here origin, it will be a straight line, right? In your plot, there will be several points. You are taking 10 or 12 data right there, right? So several points like this. So you will have the beautiful plot like this. And remember, because left hand torque is equal to right hand torque, that means this slope should make 45-degree with this axis, right? So that's all about this lab.